Thank you. So just a quick background. I went to RPI, as he said, and I got my bachelor's and master's in chemical engineering. So you might ask, why is someone in a chemical engineering background doing wind? And it's just, the way sometimes your career works out, I guess, right? So I always joke around that chemical engineers can do it all, and we can pretend to be electrical engineers and mechanical engineers and wind turbine engineers as well. So, but what I wanted to do today was talk about wind, just get you the feel of what's going on in the wind industry. Why does a turbine have 3 blades? Why is it upwind? What are the important aspects to it? What research is going on? How do these things get cited? What are the economics? So that's really what I wanted to do today. I hope to be done early enough that we have a lot of time for some Q&A at the end. And I look forward, I appreciate the invitation to speak today. So, all right, just to talk about what I want to go through today is I want to talk about real quickly the introduction and the fundamentals of wind and what are the different types of turbines and the architectures you might be able to see. I'll talk quite a bit about the resource of the wind because that's a really important thing. Obviously, if you've done any look at solar PV or solar thermal, the resource is all of it, and the wind it's not really that different, so it's really important as well. I'll get into the aerodynamics and performance and how much energy you can actually extract from these devices. Go into the cost structures behind it. So everything you see, you take this energy out of the wind, but there's this huge structure that's dependent on the loads and the controls of the system. So we're going to go through some of that. Talk about the scaling of it. Why are wind turbines the size they are today, and what's preventing them from getting larger or smaller. The considerations when you actually move these things to a park level or farm level, because typically you don't just put one up, you put multiple turbines up, and how do you actually do that? How do you put them across different places? Talk a little bit about the different technology differentiators we have across the industry. So, I'll do some stuff up front in terms of what's the wind industry converged to and why. But then I'll also talk about in the back end, where do we see differences between GE and competitors or across the industry in terms of what technologies actually are different, and we haven't really settled on one technology choice. I'll go through some of the economics of wind and how it makes it work, incentives, those type of things. And then we'll get into really what are some key technology development areas that I see, but not meant to be an exhaustive list, but just an idea of what's going on. Yeah?
Will you be able to put these slides on the website?
I will be. Yes, I will be. Yeah. I think it will be a couple days before I get that all figured out, but I'm sure they'll certainly be up. Okay. So I'm not going to do many equations today, but I'm going to start with one, and it's a very simple one. How much power is in the wind? It's a really simple equation. There's really only 3 variables. One is the density of the fluid, so it's wind, it's air, it's pretty low density fluid. V, which is your wind speed, so that's cubed, so it's really important, obviously, how much wind there is. So that's a really important one. And then the area that you're actually trying to capture. So these wind turbines can be rather large. I'll show you how large they actually get. So that's an important one too. Now we talk about how much power can you actually extract from the wind, and we'd like to put this other little piece here called CP, which is really a way of us decreasing the amount we can do. How much can you aerodynamically extract from the wind? So we'll talk a little bit about that, and I'll actually go into what's the theoretical limit that you can actually get in CP, and we'll get into some of that as well. But I just wanted to kind of talk about that. CP is the power coefficient, so remember it's the aerodynamic efficiency. Obviously, I'm going to skip over the density because I really can't do much about that as a designer of wind turbines. And I'm going to jump again to the wind speed, so that's really important. So sighting becomes really important, where I sight these things. And last is, how big do I actually make this turbine? How big is the rotor, and get into area. So those are the really big things, very high level, that are important in wind turbines. Aerodynamic efficiency, where you sight these things, and how big of a rotor you have. Now, if you looked across and just went, on Google and looked up different wind turbine configurations, you're going to see quite a bit different types of configurations. I've sort of broken them down into 3. Now you can certainly sub-break these down into a lot more. Maybe there's some other ones that I've left off, but here are the 3 main types. There's horizontal axis, which are typically what you've normally seen. There's vertical axis on the top right. They're less common, but you do see them once in a while, and I'll sort of talk through some of the benefits and challenges of those. And then there's airborne wind turbines, which are really the idea of let's get rid of a tower, let's put these things on a kite or somehow and get them up high in the air to extract some of the higher wind speeds up higher in the air. But let me start with horizontal axis. So you can really have these in two different ways. You can have the blades in an upwind configuration or a downwind configurations. In an upwind configuration, the far left up here, you see the winds coming in, hitting the blades first, and then it goes to the nacelle and the tower afterwards. That's typically what you see. Big important thing on blade design is how much these blades bend. So how much tip deflection do you actually see before, because you don't want to hit the tower, right? These blades spinning around, if that thing hits the tower, the whole thing goes down, and that's not really good for a product. So that becomes a really important design criteria for wind blades, is how much deflection you really see. Secondly, there's a different way. Let me just jump back to this first one. To make sure that's facing the wind, these type of turbines have what they call active yaw. So they'll actually have mechanical ability and sensor to make sure that they can point themselves into the wind. So they're mechanically doing that based on some control algorithms and some sensors. Secondly, you can do a passive yaw, so you can still have an upwind machine, but you can have some sort of tail or some sort of vane on the back to make sure that it automatically aligns you into the wind. So you see that more often in small scale turbines, because that's a bigger cost if you try to do that on large scale. Large scale turbines are really the top left. Now the other idea you could do is this tip deflection thing is becoming a big deal for me, because now I gotta make sure my blades are really, really stiff and they don't bend at all when I have this wind load on them. So maybe I should go downwind. So that's another configuration that people have looked at, and there's certainly turbines, a small amount of turbines that are out there that do this. The great thing is that you can allow the blades to deflect. The blades can become lighter and cheaper. The main problem that you see is right behind the tower. The wind gets really low because it has this big wake effect. And now every time that blade passes, it has a big wind, no wind. And it goes back around, big wind, no wind. And it has really high fatigue loading. And those things don't, when you're designing something with that big of a fatigue loading, let alone often an audible noise that happens every time you pass one of those blades through, it becomes a bigger problem. So you don't see those quite as often that way. So the industry is mostly this upwind type with the active yaw. Now, we'll go through when we look at CP of why we're at 3 blades, but there's certainly a lot of variations to how many blades you can have. I've seen pictures of wind turbines with 1 blade that spins around, with 2 blades, 3 blades. And you can always go up to these things you see out in the Midwest. They're really used for pumping water. Would have a lot of blades. I didn't even count it, but lots and lots of blades, right? So there's a lot of different ways you can do it. So there's a lot of different configurations, and we'll talk through some of that as well. Now on vertical axis, big difference now. They just spin around like this. So they have some sort of central pole, and they basically spin around. You can have 2 different types. You can have a type that's a lift-based type, which is similar to the horizontal. How the lift is what's causing the rotation. You see one up here, which is a lift-based type, which is typically called a Darius type turbine. There's also Savonius type, which is a drag tape type device, so it's just based on a drag. So you have some sort of cup that's catching the wind, and as it spins around, it's no longer a cup. It has a little bit of a profile that allows it to spin around. So those Savonius turbines are actually used quite a bit in anemometers for measuring wind. That's a really good way to do that. And I just quickly threw on the airborne wind turbine because you can have put these things high up in the air, and sometimes in this case I think this is actually a type of Savonius turbine up in the air because it has some sort of drag device on it. But typically you can sort of get rid of the tower as well, and there's a lot of different sort of designs on that. None of them being really big commercially successful yet, but there's certainly a lot of people looking into it. Okay, so I really quickly wanted to ground you of where the industry has converged to. So you probably have driven and seen, how many of you have seen wind turbines when you've drove somewhere, right? Pretty much everyone, right? So you see it's horizontal axis, it's upwind, you probably didn't see if it's upwind or downwind, but they're upwind. They've got 3 blades almost all the time. The rotor speed is actually going to be variable. I'll go through some look in terms of how that looks across versus the wind speed. And it has what we call active pitch. So the blades have this aerodynamic performance and they have some sort of shape, but we actually are able to have a pitch mechanism where my shoulder is, and we're able to turn them based on how the wind is. And we want to make sure we do that to control some of the rotor speeds as well as feather them out of the wind when we get high wind speeds and make sure that we don't create too many loads on our turbine. Some of the main differentiators, which I'll revisit later in terms of the trades that go off between these, are the main differentiators between some of the competitors is on the drivetrain. Do you have a direct drive machine, which is really taking a rotational speed from your rotor and going right straight into a generator? Or do you go through step it up through a gearbox? So that's one of the differences we see between competitors in the wind industry today. There's some differences in generator design and the way you actually do the power conversion. Do you do all of it or do you just do a part of it? And how do you make it grid compliant? Now obviously if you can only do part of it, that's really helpful because you have less efficiency losses, but then you may still need to make sure it's grid compliant. And then obviously each manufacturer of wind turbines has their own unique control strategy that we like to keep top secret and no one can see it. And that's typically a differentiator between us, that we typically don't know exactly how everyone else is controlling their wind turbine, but we assume that there's quite a bit of differences in terms of the control strategies. Okay, I'm going to switch over now to some basic terminology you see on wind. So there's different things we talk about that I'll throw out. I probably already have to some extent. The term rated power is really how much power the maximum the wind turbine can create. And that's not, it's specific. In this case, I'm doing it all for a GE machine, a 1.6 megawatt. So this is a big seller the last couple of years in the US. It's 1.6 megawatts. That's the maximum nominal power output. Now, we'll go through how a power curve looks like and where do you actually cap off and how does that look in terms of the rated power, but that's one important aspect. The second one is the rotor diameter. So in this case, it's 100 meters. We like to call our products the 16100. So this is a 1.6 megawatt, 100 meter rotor diameter. So 100 meters, rotor diameter. See that? I walked by the football field, right? That's the length of that football field, right? So that's really big. So now we'll talk about the scale of this. The next thing that's really important that everyone talks about is capacity factor. No one really, we will talk about efficiency and CP and those type of things. But when we really want to talk about how much energy do you produce, we always like to talk about capacity factor. So capacity factor is really how much energy did I make in a year versus how much could I have made if I made that 1.6 megawatts the entire year. So a wind turbine, if you went 10 years ago, is probably 35%, which was pretty good. And today we're pushing closer to 50%. Now, a lot of that depends on what wind resource your site you're in, and a lot of other site-specific pieces, but you're on the order of 40 to 50% on capacity factors. Now, compare that to solar PV, which you're probably around 20, maybe 25% if you're really good. And on the far end of the scale, if you looked at a base load natural gas power plant, it might be 90%. So you're sort of in between the two. You're not really base load, but you're not really always variation all over the place. You're still producing quite a bit of power, and you're getting a pretty high capacity factor. Another thing when we talk about wind resource is the average wind speed. So we often like to very simply look at our wind speed site and say how much wind is at the site, and we just say what's the average wind speed. Now it's not as simple as that, and I'll go through some of the looks at how is it distributed and what are the details in that. But very simply, if we're just looking at a site and understanding if it's going to be good for wind or not, we often just look at what's the average wind speed of a site. So if it's 7.5 meters per second in this case, that's actually pretty good. You could probably make a pretty good economic case in the US. In the US, most of the time, if you're above 7.5, you're a pretty good economic case. Most of the stuff that's developed 5 or 10 years ago was really closer to 8.5 meters per second. If you looked at, say, Germany, where they have lower wind speeds, they'll do it at 6.5 meters per second. But if you drop below 6, it's really, really hard to make the economics work. And in the US, if you drop below 7, it's still pretty difficult to make the economics work. So that becomes really important. Associated with that is some sort of turbulence intensity factor. So we'll go into a little bit of that detail as well, but that's important. And we have an IEC class. So that's typically, we design a wind turbine to an IEC standard, and they have different wind classes. So an IEC 3 will have a wind speed of 7.5 meters per second. I think that's when I have it 2, which means it's an 8.5 meters per second wind speed site. That's associated with some other distribution factors in terms of the maximum wind speed you might see at the site, what's the maximum gust, what's the maximum kind of average wind speed you'd see to design for. So We'll go into some more details on the IEC standards as well. All right, so I talked about utility scale wind turbines and the 100 meters being really big, but I think there's really two major points that makes this technology different than anything else that we've done. Any other energy generation technologies is the size, right? This thing is absolutely huge, right? So I'm trying to extract energy from a fluid that has a density, and the density is air. So it's very, very low. It's like 1.2 kilograms per meters cubed. Really low density. I need to make these things massively big. So our 16100, 100-meter rotor diameter on top of an 80-meter tower. So the hub height of the tower, the height of the tower is 80 meters. So this is really big. The weights of these things are not, these are, rotor's 50 tons. The nacelle on top of it's another 60 or 70 tons. Your tower is huge. It can be, even bigger if you don't go a steel tubular tower and go to a concrete type tower. It becomes even bigger in terms of mass. Yes?
Just trying to understand. So it's the lower numbers applied to that 1.6 megawatt unit that you showed us in the previous slide?
Yeah, so yes, about. So we have a suite of products that I could have chosen from. So instead of setting the specific ones, but this is more on the lower side. So we have some products that are a little bit smaller than the 16100, more historical types of products that we don't make anymore, but they're sort of the lower end. So, but the 16100 is on the lower side of this. And then when we get to our bigger platform, which is typically for Europe, and I'll talk about why we have different products for Europe and the US, we'll get into why you're on some of the higher sides. But substantial height too. Look at this. We have the Hoover Tower here on campus. I walked over and got to see it before I came here today to see how big it was. It's pretty tall. But if you think about our 2.5 or 120 machine, it's about double the height. So imagine how big that thing would look like on this campus, right? So these things are massively sized. So just remember that when we're looking at all the different technologies. If you're trying to prove out a new technology, how do you do it at scale, right? It becomes very difficult to have a test bed to do a full-scale test on wind. If you're trying to do a new aerodynamic design or anything like that, it becomes very expensive because these are really big machines. The other thing I wanted to point out was not just the scale and how big these things are, but also, to some extent, how simple they really are, right? If you looked at our blade and you looked at a wind or a airplane wing, right? Airplane wings have these flaps all over the place, and they're doing all these different things. This thing is one, solid piece going all the way down, right? This solid outside shell. So it's really set up to be very simple. And any sort of actuation devices or anything you want to add on that are new technologies, it really needs to buy its way on economically because it really favors low cost, simple designs for maintainability and low cost.
Do you use wind tunnels or anything like that to scale for a smaller prototype?
We have used wind tunnels, and there's certainly value in doing that. Now the question is to get to the right Reynolds number, you often need to rotate these things a lot faster to get higher tip speeds and to do the right, to do the right scaling. But that becomes a challenge because that balance is really difficult in how you do that scaling because the wind tunnels are really not that big, right? So you're trying to make this little miniature wind turbine and you run it in there and you're trying to extract the results, at a scale that's hugely different. Yeah.
How do they handle shipping? How do you move these?
Yeah.
On the other side?
Yeah, big problem, right? So all of these components right now are really also designed not only for these loads and all these things, but how do you ship these things around, right? Because you need to ship these things to the, somewhere, this mountain pass in California, right? Not exactly an easy place to get to. So typically, up till now, most wind turbines are one single blade. We roll down the highway. We made it just enough so when we have to make that sharp turn in that small town, we can do it. And and pretty soon we might need to tell this person we're going to take their porch off. I don't know. Maybe we'll rebuild it afterwards, or maybe soon we'll have to. We're going to move your house. It becomes more and more of a challenge, right? There's a challenge for the blades, obviously, because of the length. There's a challenge for the towers, not for the length because we do split the towers, but in terms of the diameter, right? And the same thing with the nacelle, which is the box at the top, also has dimensional limitations on it that we typically do. So that's a big problem, and it becomes an even more exasperated if you try to ship something in India, right? So you're trying to ship this in India, you have all sorts of different constraints. You have different constraints just between the US, different parts of the US and Europe, and there's all these different constraints you might have on your system. But when you start to go to places like India or somewhere else where the infrastructure is not as well set up, it becomes an even bigger problem. All right, so wanted to show you a cutout of really, I did say it's so simple, really simple things, but I'm going to cut this out to show you that there are quite a bit of moving parts. I talked a little bit before about the pitch blades, so you can think the blades coming out of here, that's the mechanism that's going to be able to turn the blades. It's connected to the hub, so the hub is the middle thing that's going to rotate around with the blades, but it's going to be the structural piece that holds it all together. It's going to run through a shaft into a gearbox. So this is a case of a geared one. If you didn't have a geared one, a direct drive one would go straight into a generator. But in this case, we're going to go into a gearbox where you say you're going to increase the rotational speed by, say, 100x, go into a generator, you create your electricity, you do some sort of power conversion, which can either be up tower or down tower. There's some differences between that. And you run it down the tower, collect it at the grid, send it out to utility, and it goes to your house. There's a lot of other pieces here that are really important as well, especially when you add up the cost, right? There's a lot of structural pieces that are the hub, the bed plate, which the whole drivetrain is going to sit on, the tower. Those are really expensive pieces that are all really there, just structural pieces. So how do you how do you handle loads and controls to minimize the loads those things have to maintain to make them low cost? And then also, how do you do mechanical design enough that you can really reduce some of the costs of those components? So, I talked about it before. There's the big aerodynamic pieces of the blade. There's mechanical aspects, structural pieces around the blades, rotor, bed plate, tower, and there's electrical pieces in here as well. So there's quite a bit of different engineering that goes on. But at least to get you a feel of the cutout of what's inside one of those nacelles. All right, I'm going to switch now to talking a little bit about the wind resource, which is a really important piece. Remember, it's V cubed, so it's probably the most important piece. So if you looked at the top right, this is the NREL map of the US, of the average wind speed. Purple is really good. Green is really bad. So a couple things to notice here. The Midwest is great, right? So they have great wind speeds. Places you might not think about, Illinois is pretty good. And really up into Michigan. Even a little bit through New York and New England. There's nice patches in western New York and northern New England that are pretty good. You might look at California and say it's really not that good, but there are patches. There are nice, really strong wind resource patches in different places. The other thing to really notice is if you looked at the southeast of this country, there's like nothing, right? The southeast of this country has really poor wind resources, onshore at least. So it's going to be really difficult to make any economic wind turbines go up in these states. So that's a really important piece, specifically when you get into the politics of wind and how do you do incentives, because all those representatives from all those states say, what's not benefiting me, and my taxes dollars are going to support it. And it's not even a Republican-Democrat thing as much as a geography thing in terms of the wind resource. So it's a kind of an interesting geopolitical type of thing going on there. Now, I also threw down the installed wind map that I put up, and for some reason I decided to overlay it a little differently, but the red color is where you get the most wind installed, and you see a lot of wind installed, California, Texas, and Iowa. So you say Texas and Iowa make a lot of sense because they're right in the middle of this great wind resource. To some extent, why is Nebraska and South Dakota kind of not doing as well? But in California and the West Coast also looks pretty good. Yep.
Mention offshore?
Yes, I will mention offshore. I also mention it a little bit right now. So offshore certainly has better wind resources, right? The wind resources, if you look offshore at any of these places, the wind resources look a lot better. Now the trick is that when you go offshore, you've already added a lot more cost, right? So you're getting a better wind resource, but your costs are shooting up because now I have to put this big foundation in, and I also have to run some sort of transmission lines through water, and I have to do all this collection between different turbines because I'm probably not going to put one up. So when I go through the economic portion, I actually have a roll-up of the estimated LCOE from the DOE between the two, and it's in the right order of magnitude from what I've experienced in terms of the difference. So you can see some of the differences in terms of the challenges for offshore to make it economical, right? But you certainly, if you looked at it at a map and overlaid the offshore wind piece, you would see great wind resources offshore, pretty much along each of the coasts, and to a lesser extent, maybe to a lesser extent in the Gulf of Mexico, but really along the coast you'd see really good ones. Yes.
Can you talk a little bit about Iowa compared to the states nearby?
Yeah.
That seems an interesting story.
Yeah. So it is also could be, a little bit of just a step change on my graph, but it is doing a lot better. Specifically, Minnesota, Iowa, and Illinois have done really well, and I think it's a combination of the resource which you have, but instead of the states next to it, you see a lot of support. One, they have a lot of manufacturing capability there in those states, so there's a lot of blade manufacturers there that GE purchases some blades from, or different places. So obviously, not only if I'm a representative of that state and I want to make sure that wind goes in, I've got all these jobs that are created here, and now I can also supplement that by adding energy as well. It becomes a really nice thing. So it's a combination of this wind resource and localized incentives, and they may not even be economic incentives like an RPS standard that you might see. Like in California, certainly what's driving it, but in Iowa it might not be as much as the political forces saying, look, I've got all these jobs here that are supporting this, I might as well support the industry as well by providing some of these projects as well. So there's some pieces of that going on. But I mean, one of the other interesting things is the great wind resource is somewhat isolated from where we use our energy, typically along the coasts. So there are a lot of transmission issues. And if you want to put up a new project, you need to make sure that the energy is going to be transmitted somewhere it's going to be used, right? So that becomes a holdup in a lot of cases in terms of, oh, I want to put a project up, but I don't have that transmission line put up, and I need to make sure I have that. So that can become a sticking point in some project development. All right, so to characterize wind, remember before I said 7.5 meters per second, that's good enough, and we're just going to use an average wind speed. Well, it's not that simple. In the upper left, we actually look at how is the wind distributed across different, and the way we talk about it in wind is we bin it. So we're going to put it in bins, so every 1 meter per second, and 2 meters per second, 3 meters per second. We're just going to look at the average time that's within those. You can see this nice distribution. This is the one I drew, which is a Weibull type distribution. So that's typically what wind, if you went to a site and measured it, it would more or less fall within some sort of Weibull type distribution. Now there are outliers to this case, and every site can be a little bit different, and actually can be different than this. But that's typically what's mostly seen in wind sites. Also, there's directional changes. So often you'll see it's mostly unidirectional, but there's different directional changes in terms of where's the wind coming from. This is important if you see huge amounts of differences in wind direction, specifically, not even on a map like this, but time-wise. Like if you're in some sort of weird mountain range where you have some valley and you might get some wind shooting from different ways, that can become a big problem because now I don't have enough time to yaw back and forth to really capture that wind. So that can be a kind of a red flag in terms of the siting of that wind turbine. Even though you might have a great wind resource, if it's shifting around quite a bit, specifically on a really short time scales, it becomes a tough thing for some of these wind turbines to handle. Another thing is that, and you probably know this if you went to a tall building sometimes, it's always windier at the top of a tall building. So there's a thing called wind shear. If you stand around outside, it's not as, you go up, it gets windier. And so that's, different places have different amount of wind shear. I think the shear we're talking about is how much increase in wind do we see as we go up. So we look at it in different ways, but we have a simple, I'll show you later, a simple example of how high should I put a tower, and it depends on how much is this increasing, how much is the wind speed increasing as I go up. We also look at how turbulent the wind is. Remember, it's not this nice smooth field of wind coming in. There's different patches that are going different speeds, especially when I have something as big as the rotor I have. So you're seeing a lot of different turbulence. So you need to factor that in terms of not necessarily the performance of the wind turbine to some extent, but really the load's impact, right? So I'm going to might see, this blade might be getting hit with a lot more wind than something up here, and it might be shifting around quite a bit as it just moves across different time variations. And then obviously, everyone thinks about, if I need to design this thing, I need to make sure it doesn't fall over or break when I have a high wind event. So that's really important too. So really understanding the site characteristics is an important piece. So if a person was going to go develop, a wind site here at Stanford, they would put up some tower and they put a little measuring device up there and they collect data for a year, just to figure out all these things of how much wind do I really have here? Is it really worthwhile to do that? Do I have any strange interactions going on? So there's quite a bit of data collected. All right. Now we're going to get into the aerodynamics and performance. So in the aerodynamics, a good way to think about the aerodynamic performance or the power coefficient CP is to really think about the wind blades acting as a permeable disk. So we talk about this as this actuator disk theory where you have a disk that's extracting power out of the wind. And if I did that, I could see that I'm going to have an upstream velocity that's pretty high and I'm going to extract some amount of energy out of it, and my wind is going to be less, V2 is going to be less than V1, right? So I'm going to be extracting some sort of power. It's interesting in the fact that if you looked at a conservation of mass, I need to make sure that as I go between those two, I'm going to be increasing the size of that field. So now I start out with a narrow cylinder, and it's going to increase as it gets bigger as the speed slows down. And the speed doesn't slow down in a step change, right? Because we need to make sure that all the air continues to flow through. I can't have stagnation of an air in a free stream. I need to make sure that stream's continuing. So actually the wind speed begins to slow down, if you looked at this part, before it hits the rotor or the actuator disc, and continues to slow down to a little bit afterwards. So across the disc, I'm seeing very little change in wind speed. I can think about really three different wind speeds, one here, one at my disc, and one downstream. Now what happens is you have a big increase in pressure, which is pushing some of the air outside of this disc. And if you go through the derivation of a factor called A, the axial induction factor, what it is what's the speed at D versus what's the speed at V1, right? So that's really what A is. And really, if I looked at it V2, it's really 2 times the A, because I've defined it as half my velocity reductions upstream, half of it's downstream. So now I can actually substitute that into my power equation and come up with actually what does my power coefficient look like in terms of my axial induction factor. So I have this nice CP is equal to 4A. I think this is the last equation I have up here. And we have this equation, and if you just plot it across axial induction factors, you can see that it maximizes at around 59%. It's actually 59.3%, and that's the Betz limit. And no wind turbines ever exceeded that. In fact, state of the art in wind today is around 51 or 52% of what we see. And most turbines will run somewhere, actually, if you looked at very simply, this is how much energy I'm extracting, is this light blue line. This dark blue line is really, you can think about it as very simply, this is the thrust, or to some really simple equation, how much cost do I have in my machine, because I have to accept all this thrust. So I don't really want to continue up this. I don't want to be on this side of the optimum. I actually probably want to be on this side of the optimum where I reach almost all the way to the maximum CP, but I've minimized the amount of thrust I need to expose and how much cost I have to have. So that's typically, if you see a wind turbine today, it's probably running around an axial induction factor of 0.3, give or take. So if I looked at the CP, so CP now is on the y-axis, and on the x-axis is a new variable I'm calling tip speed ratio, which is really the ratio of how fast are my tips moving versus how fast the wind speed's coming in. Now, remember that the limit I actually have is at 59.3%. And if I looked at it, and this picture doesn't have the 3-bladed machine, but I'll talk to it. The horizontal axis has the highest peak. And if you went to 3 blades, it goes a little bit higher. And if you went to 4 blades, it would go a little bit higher. And you went to 5 blades, it just kind of get a little bit bigger and a little bit bigger, and you get a little bit closer to the Betz limit. But every time I add a blade, I add cost. Yeah. Every time I add the blade, I add cost. So everyone has really converged around the best trade between the number of blades and the cost associated with that, and the actual performance benefit. Again, CP is 3 blades. Now, also, you can look at this vertical axis Darius rotor. You can get pretty good performance, maybe 40%. But that's typically to get that installed instead of a horizontal axis machine. you would now have to be significantly lower cost because now I'm having a lot worse performance and about energy extraction. So it becomes a really difficult thing. And you really don't see any Darius rotors in utility scale wind. You only see them in residential places where, you know, it may not be as important. The true economic drivers aren't as important as maybe the physical look a little bit. You know, some other things might go on. So you might see that the only place you might see a Darius, and there is some active research going on, is for really large offshore wind turbine farms. So, I mean, not at GE, but at Sandia, they have a big program at looking at vertical axis, and the idea is I can have significantly lower loads on my foundation, which is a huge cost offshore, by going to this Darius rotor. I sacrifice some of my aero efficiency, but I can do that because I'm trading that huge cost advantage off. So that's the trade to shift down on this curve. You really need to have some sort of huge cost advantage. Just a couple other ones. You know, that Savonius rotor, I think this is actually, I don't know if I believe the peak of this. Actually, I think the peak of it should be a lot lower. I think most of the Savonius rotors that are out there are only around 15% on the CP. They're typically only used for measurement of wind, which is actually really good for doing that. So you see them, you know, as the way we typically measure wind on top of a wind turbine. You'll see this little thing spinning if you get really, really close. Maybe you have binoculars. The other piece is, you know, this one that we see in the Midwest with all the different blades I showed before spinning around. Actually very low CPs, but they're not really made to produce power, right? They're made to produce thrust. And if you looked at this on a thrust curve, on a CT curve, you'd see that they're really high thrust because they're trying to either pump water or, you know, use as some sort of mill or something. So it's really designed for a different type of case. So that's why we've typically, in the utility scale wind, we've gone to 3 blades, and why it's really difficult to switch that to something else. Okay. All right, so if I wanted to take a wind turbine now, everyone who makes a wind turbine publishes a power curve. And a power curve is just real simply how much power am I going to have from this wind turbine at different wind speeds. Now, I've overlaid in the green, remember this distribution of wind, this Weibull distribution, so that's what I have there. And I started out by saying if I just had a wind turbine of, I think in this case I have a 120 meter wind turbine. What if I just decided to how much power is in that wind? That's the dark blue curve. You can see it just continues to go up at a slope to the power of the cubed, right? Because it's all dependent on that rotor speed cubed, or the wind speed cubed. Now, what happens in real life? So our 25120 is this light blue curve. So all this down here, this difference that drops it down is due to efficiency losses. So that's the losses on the CP. It's also some losses that you see in terms of the electrical efficiency of taking that rotational speed and transmitting it into electricity. So that's your gearbox losses, your generator losses, your converter losses, whatever collection losses you might have going out of the turbine. So you see a little bit of reduction there. But the interesting thing is that it stops. It stops and cuts off here, right? So that's a thing that happens on wind, is because if I continued up this curve, it really, all my loads are going to increase with that wind speed. So my loads and my costs of my turbine are going to explode up if I follow that dark blue curve without adding that much of the wind that I'm really going to extract power from, right? It's a relatively low percentage. So instead, I'm going to cap it off to manage the loads and therefore the cost of my wind turbine, and I'm going to flatten it out. So this is where I start to pitch my blades. I destroy all my lift, and I've just feathered my blades out, so now I can just have a very, you know, just keep at, in this case, 2.5 megawatts. I go up to some sort of wind speed, and in most cases for wind, it's either 20 or 25 meters per second, and then I say, you know what, it's not worth it anymore, and any of this point, it's going to be, there's no more real energy often, and it's not going to happen that often. I'm not going to extract that much energy. I'm just going to drop out and protect my turbine in terms of any extreme events. So that's typically what happens. So if I want to improve the aerodynamics of my wind turbine, improve the CP, it only really matters here. My CP, if I improve my CP with my blades, it doesn't matter out here. So it only matters in this region. And that's an important point. There's one other little thing that goes on here is you would expect this to be a nice sharp point that came over and closed off. But in order to minimize some of the thrust that we see on a wind turbine, we have what we call a peak shaver, which is going to shave and curve that place off so we can handle some of the load changes between those regions a little bit better. Yep.
What's a typical range of operating rotational RPM of the blade?
Next slide. All right, perfect. All right, no, 2 slides down. So hold that thought. I'll get to it, I swear. All right. So if I wanted to look at a wind turbine is only as good as the annual energy production. So if I take this is a really simple chart. We'll take top left is our wind distribution. I overlay my power curve, and I come up with an energy yield. And that's really what we do on all of our wind turbines. And basically any project we're looking at doing for a customer will do this too. They'll say, I have this site that has this wind distribution. I'm going to look at these different types of products that have this type of power curve, and this is how much energy I'm going to produce. So this is really a look here of the energy yield. The interesting thing is that most of the energy you're creating is probably between 8 and 12 meters per second. That's a really important point. So between 8 and 10 is really important on CPs, but between 10 and 12 is really important in how you handle your peak shaver and some of the control aspects you have. So that's an important point. Okay. All right, this is where we get into rotational speed. So very simply, I'm just going to step through this in a few different places. This is our 2.5 power curve. So you see 3 different parts. Right here, no power. We're not even going to do nothing. We're not even going to start. We're not going to start until it gets to 3 meters per second. Then what we're going to do is we're going to call a cut in. We're going to start rotating our wind turbine and producing power. We go up the power curve, and then we're going to cut off. Now, if we look at, this is our speed of our wind turbine. So in here, we're going to slowly get up to rotational speed. Along this point, we're all going to increase our speed. So now we're going from anywhere from 5 RPM up to about 14 RPM. A little bit before we get to our rated wind speed, we're going to cap that off, and we're going to keep a constant RPM. So that's the line right here. We're going to keep a constant RPM, 14, all the way out to where we're going to cut off. So that's what's going on with the rotational speed. If I looked at a couple other pieces, so at my pitch actuation is in the green. So my pitch actuation is what's happening with my blade pitch. So all the way up, I'm very finely pitching it to make sure that I have really good aero CPs. I have it really perfectly, and then I get to a point, in this case 10 meters per second, I'm going to say, okay, no, I'm going to start to feather out and make sure I handle some of these loads. And it's really important that I don't do it at 11 and I do it at 10, because if I looked at my thrust, otherwise my thrust would have this big peak to it here, and by pushing out my feathering of my blades to 10, I can handle that and actually bring the thrust down quite a bit. So that's an important point, and that's what the peak shaver region is really doing. It's just managing that peak thrust that's going on in the wind turbine. So does that answer the question on rotational speed? Yep. All right, that's really around performance, but now we have to talk about the other side of the equation, which is the cost of a wind turbine, really, really driven by load. So, anyone who does these analysis, let's figure out how we design these wind turbine components. How do we do that? Do we measure a big wind turbine on its own? No, we do a big simulation, because these things are massively big, and if I wanted to make a 115 meter rotor, I'm not just going to put it up there. I'm actually going to have a simulation of how much loads I would actually see. So we have really big, really detailed models of how to do these simulations of different wind events on these structures. That drives down into structural design. Think of it as a blade. These are the aero properties I want to have. We go through this load simulation, and it says, okay, these are the loads you're going to see on this blade. They're different regions of operation. So now you have to mechanically or structurally design something that can handle all those loads, and that comes out to a cost. This is all really driven within a framework of a certification body. The industry has really gone around the IEC standards, which is, I think it's down here somewhere, International Electricity, I got it, some commission.
Yeah, before you do the simulation, of course, you take some data, right?
Yeah, absolutely. So, but often on the IEC standards, they'll say, you know what, instead of designing it for that one specific site, I'm going to come up with an overall idea of this wind turbine. You can design it for an IEC class 2, 8.5 meters per second. The maximum speed you're going to see is 42.5 meters per second. You can do it at some different turbulence intensities, and we're going to define all of these different cases you have to handle in terms of, you're running and all of a sudden you need to, you lose your grid connection and now you have nowhere to put the energy and you need to brake. And all these different, or you're going to see a big increase, a big gust in wind, and they define all of those so that now you can design your turbine to meet these standards and then go to a site, take the data and say, does this turbine that I designed for this class 2 fit this site? Will it be fine or not? And that is an important second step because it's not always the case. So you might see high turbulence intensity places which are very difficult, but it's to the point of you can't design a turbine for every site, right? You can't have a specific turbine design optimized for each site, so we only have so many products we can actually support in terms of doing this. So IEC standards is a way to do it. It's also really important because these things are very expensive, right? So almost all of the costs associated with wind is capital cost, and so typically you need to get it financed if you're trying to make it, and it's really important to be bankable, or financially bankable, or be able to get a loan for it. So one of the things is if you don't have this IEC standard, it's really difficult to prove that the technology is not too risky for them to invest in. So basically the whole industry gets certified via the IEC standard. There are a couple other ones like the DIBT, which is just slight modifications off the IEC that's specific for like Germany. So there are wrinkles in certain locations in terms of the right standards that you need to do, but typically the IEC gets you really, really close to almost all of it. So following on to your question, this is just sort of that piece of now you design a turbine for an IEC class wind site, but now you need to go to make sure that at the site I can actually apply that wind turbine, right? So site-specific mechanical loads analysis, or we call it MLA. You go into how are we proposing to lay the turbines out on this farm? What do I think the distributions of winds are going to be at that? What's the different turbulence intensities I'm going to see at that site? And now I can go through and do an analysis of can I say for sure that this turbine, which is designed for this class, will work in this location? And sometimes the answer is no, and you need to either get rid of that turbine, or maybe you need to move that turbine to a slightly different location in the farm. So there are some movement around in terms of okay, this is a very turbulent area. And in fact, going back to the place where I talked about the wind direction changing, you can think about it, I'm trying to site a turbine in, and I'm getting all this turbulence in it, and it's a little bit more laminar. If I move it over this way, it's going to be more important for me to do that. So this is a way for them to do it. So they do create quite a bit of wake effects, which are to some extent not well understood. There's a lot of research going on in terms of wake propagation. Typically, the wind turbines are sited 5 rotor diameters apart from each other, and the idea of that a lot of the turbulence caused by the wakes have now smoothed themselves out to an extent. So you get a lot of you do see some differences in terms of the turbulence on the back end turbines, but not that much if you space them out far enough. There's 2 problems. One is the turbulence caused by it, but also the other problem is the back turbines are seeing a lower wind speed, and that lower wind speed now is really brought down the amount of energy that back turbine can produce. So there's that aspect too. And how do you site these things to do that? I have a really fun picture that's actually pretty famous in terms of wind turbines. A little bit later they'll show that. All right, real quickly, I'm going to talk through some of the how you do scaling on wind turbines. Why are they the way they are? So generally, there's this thing called the square cube law, which would make you think that you shouldn't make a wind turbine big at all, right? So my energy capture is based on my rotor diameter squared, but my loads and therefore a lot of the cost structures I have in a wind turbine really scale closer to rotor diameter cubed. Not exactly, but I mean for a general extent, it's a generality that's relatively true. So in that case, you say increasing my rotor diameter is just I'm going to increase my cost faster than I can increase the energy capture I do. But we all know this is not the case. We actually see wind turbines out there because there are some economies of scale that exist. So if I had all these little tiny turbines and I had to install 1 million of them around, it's going to cost me quite a bit to go do that. and make sure that they're all installed. So there's quite a bit on installation, economies of scale. There's a big economies of scale on the balance of plant. So how many little tiny concrete pads do I need to pour versus just a few big ones? The big one that a lot of people don't think about is if I'm assuming that I need to get up high enough in the air to get away from a lot of turbulence created by trees or anything else or vegetation, I have a certain amount of hub height I need to get up. So that the tower becomes quite a big portion that you already need to have a sunk cost into. So that already gets you to a bigger size turbine. And really, one of the big problems with residential wind is the cost, and a lot of the cost is really these things: installation, the BOP, the tower, of not moving this thing to the height of a utility scale turbine, but you moving it high enough off the ground, it becomes really kind of expensive. And there are some economies of scale in the power electronics. And based on all of these economies of scale, you really have seen where the thing lands. So you have this decreasing cost by all these things, and you have this increasing cost based on rotor diameter above. You'd think that it's going to settle out to some sort of optimum, and that's sort of what it does. It's somewhere around 1 to 3 megawatts of rotor diameters of 70 to 130 meters is sort of where products are typically done. Now, we'll go through some of the other pieces of how technology can shift those things, and does shift it, and you see changes over time, but you don't see big step changes in terms of all of a sudden we have a 200 meter rotor diameter and we have a 10 megawatt machine. This is, the real simple look at it. I decrease my BOP cost as I get bigger. My turbine cost gets a little bit bigger, and I really want to settle into some sort of optimum. And with technology, I can, and this is being really optimistic, I can bring my technology so my turbine cost stays the same as I get bigger. And it's not really always the case, but I can shift my optimum. So, technology advancements don't just make their way onto a wind turbine and keep the wind turbine the way it is. Every time I add a big enough change in a technology, I might want to optimize to a bigger product. So you'll see, historically, 6 years ago, GE would sell in the US a 1.5 megawatt with a 77 meter rotor diameter. And today, our big one is a 1.7 megawatt with a 100 meter rotor diameter. So now we've gone from a 77 all the way to 100. And that's really been done by injecting technology. And that we could have injected it on the 1.577, and to some extent we did, but we've realized, we can take a lot of the same components and just scale it up now and put these bigger blades on it. Why don't we do that? So you'll see the technology has the two different things. It pays off on the current products, but it also changes your product, your optimal product size. Yep.
You start to drag it back to the other 50 rotors. As you get bigger and bigger, you're sweeping out higher velocity.
Yeah, so important point on when you scale these things up and you get bigger and bigger rotor diameters is how fast is that tip moving. And typically the limitation, you do get into places where you need to look in terms of the aerodynamic performance at the tip. And there is work going on in terms of how do you model that and make sure you get the right structures on that. But it also is very often limited by the noise created. So there's always noise constraints that are associated with that. So typically as you scale up, I'm not going to let my tip speed increase that much unless I can add some new noise abatement strategy on my blades, right? So if I have some noise abatement strategy, but you can think noise is going to scale with, it's going to be a function very simply of the tip of speed of my blade, right? So if I scale up bigger, I'm going to keep my tip speed the same, which means I'm going to rotate slower, which means I now have more torque going through my drivetrain, which is going to increase that quite a bit in terms of cost. So there's those trades as you go up as well. All right, so what I do at the Research Center is wind systems engineering, which I always have to put a slide in of what actually I do. We have a lot of researchers, and there's a lot of research going on at the component level. And what I like to take a look at is how do you translate that in terms of how does that impact the product? How does it impact other systems? As I'm increasing the rotor because I have this new blade material, now I can go bigger. What does that mean for my gearbox? What does it mean for my overall wind system plant? So that's really the work that I do is how do you look at trading off between the rotor diameter and the rating, your hub height, your tip speeds, and you really need a system level way to look at across all of these. Because if I just focus on improving performance of my blade and not understanding as I improve that performance of the blade, I'm going to add 2% improvement on the performance, but I'm going to add 10% on thrust, and that's going to propagate all the way through my wind turbine in terms of cost. It's really important to understand all those trades, even when you're doing a lot of detailed component level technology development. So this is just a quick look at how do we do a height optimization. So you go to a higher, taller tower, you get better wind speed, you get reduced wind shear, potentially reduced turbulence. So this is all great things, but every time you add more metal, it's going to get more expensive, right? So there's a trade, and you can do a very simple, this is a simple way of doing it. There's obviously a lot more advanced ways, but this one, it can generally be translated as a power law, which you take, a reference height and a reference wind speed, and now if I go to a new height, I just multiply it by an exponent. The exponent is typically around 0.14 to 0.2, so you can see you get some increasing average wind speeds as I go up and down in terms of hub heights. So now you can start to do trades in terms of if I know how much cost I need to associate with a taller tower in terms of the tower and the foundation, and I know what my wind speed is going to do as I go up and down, I can run an optimization on this and tell you, okay, the tower shouldn't be 80 meters. You should actually, it would be much better to have a 92 meter tower at this location, right? And you can start to do those trades in terms of the right height for the different towers. So that's just one really simple wind systems type of trade-off you can do. Yep.
Can you touch upon the base size, its diameter, construction, as compared, associated with the wind speed at a certain area?
Yeah, I mean, so the construction of wind turbines is, really, say you're going to make a blade. Typically, blades to most blades today are made in one piece. So you have a big shell, you have the big transport of these blades. So you've designed this whole system. You design your whole product line, your whole product around this one blade length. So it's going to be, say, I have this 50-meter blade, and I need to make sure I know how to ship this blade. I need to know how to manufacture this blade, which is not a small challenge on itself. Now, when I get it to site, I need to make sure that I understand the impacts of all these different things it might see on site. So it's going to see turbulence. Did I design it for all those turbulence? What's it going to see in terms of all these things? Do I need to do? Wind turbines are not without maintenance. I mean, they're relatively low operation and maintenance costs, but they're not without maintenance. So you see, do I see any cracks appearing on these things that are seeing high fatigue loading type of locations?
I asked you particularly about the base, the size of the base and the construction of the base.
Oh, the foundation? Yeah. So the foundation, certainly, it's another engineering piece that you need to do. Typically, the way the foundation is sometimes in people like GE scope and sometimes not. So we do have some designs for foundations that are associated with some IEC standards, but you would have to go through the same type of things. And basically, you make a pad. You have rebar put in. You pour the concrete in, and you have some. That's the basic foundation. You've done all your structural analysis in terms of the loading. Typically, the most important one is the loading on an extreme wind event of the turbine tipping over is really the thing that typically sizes the foundation. So that's, that has to be done as well. Sometimes it's done by the manufacturer. Sometimes it's done by, a third party. But it's an important piece, and it's, balance of plant costs like the foundation, which you can't discount in terms of design roll-up of cost of a wind turbine, right? Because you need to have that, otherwise it's just going to fall over with the slightest breeze. All right, so I'm going to have one last thing on my thought about systems engineering. I think a lot of technologists, and for good reason, focus really on really detailed component level technologies, right? So I'm going to focus on the efficiency improvement I'm going to have. I'm going to focus on what are the loads I can take out of this one component, or what are the materials I'm going to add into the blade. But you really need to, and then there's this other aspect of what customers really care about. They don't care about what's the material in the blade typically, right? They're not going to really care. They just want to make sure it doesn't fall apart. They want to make sure that when they run their project economics of it, that the LCOE, the NPVs, the IRRs make sense, that they can look across the fleet of all the different things they have and they're having no big problems on O&M. So there's this, big gap between those two, right? The looks of where the technologists like to look and where customers and people like banks and people who are going to finance these things look. So really the way that system value optimization is to fill in some of those gaps. How do you take the detailed technology components and roll them up in terms of what does it mean at a turbine level? What does it mean at a farm level? What does it mean as I go up in terms of not just I've changed this material, what does it mean for O&M? What does it mean for the life cycle cost of this blade? So that these are the type of things we're trying to do in terms of systems engineering of wind, is support a lot of our component technology work that's going on in terms of not only understanding how this propagates to the system, but providing the right feedback for them to understand the trades they have to make, because there's always trades you make with technology development in terms of how much efficiency do I really try to grab versus cost. All right. Yep.
So actually, when I first saw it, I had a different interpretation of farm. I'm an Iowa farmer. What percentage of my cornfield does this take?
So it's a good question. So I don't have the thing. I know. Yeah. So that's good. Yeah. And in many places, the farm is the right terminology because it's often put on farms, on the cornfields. It depends on how much land you own, right? I think I've seen cases where you have places where you have small farms, which go into a co-op in terms of supporting a wind farm. So you may have 1 or 2 turbines on your farm, and maybe your next door neighbor has none because of the locations, but you've all kind of set it up and made your big co-op available, and the next person has 3, and that there's a big co-op available in terms of supporting that wind farm, and you guys are taking advantage of being able to use the land through a royalty or some sort of other payment. But it often does come back to farmers, and these often do look like farms because of specifically in the Midwest.
I guess the question is, so it's like a 500-acre farm that's flat, and what percentage of my land would actually get used that I could still grow stuff on?
I think it's really small. I don't have the number on the top of my head, but I'll tell you that.
I've seen pictures where it seemed like the footprint on the land actually wasn't that big because of the spacing between the blades.
Yeah, I think it's going to be relatively small. There are going to be roads that they're going to have to build between those to move, different pieces of equipment that may need to be repaired. But typically, it's relatively small in terms of the footprint you need in terms of an acreage piece. Obviously, not when you look up into the sky. It's going to dominate the skyline. Right? Yeah.
So we have some turbines farms in California, and that's like cornfields and one on the peaks of our ranges. So, whose land is it? How do you get to install your unit, and then you walk away and someone else does the O&M and you go on to the next one?
Okay, so there's 2 different pieces to this, right? This is really good questions. It's someone's land, right? So it depends on whose land it is, and it's not GE's land, typically. Most, 99.5% of the time it's not GE's land. And often it's across a few different people's land. So either that land has to be purchased from them, or they basically lease it. The lease structure may take the form of, you're going to pay me this much money per year. Or it may take the form of how much energy you extract, you're going to pay me this much. So there's different ways they can be extracted. I think that the second piece of your question was around. Who does the maintenance, right? So, yep. So I'll say it like this. So, right, these wind projects typically want to run for around 20 years in terms of a time frame. You will see GE will support it, and we'll have contractual service agreements that we can do. One, we typically have a warranty period, say, a number of years that we'll do the, be under warranty and we'll do the repairs. After that, we do offer contractual service agreements that we can provide all the operation, all the maintenance that goes on to these wind turbines. Or you can go to a third party. There's third-party companies that provide maintenance, and they understand how to maintain these wind turbines as well. So there's different ways that they can do it. So there's sometimes GE does it, and sometimes it's the customer finds it's better. Oh, I know how to. I've been working with this other construction company or this other company, and they really know how to do a lot of these repairs, and I'll just make sure I have all the parts ordered, basically. So you see a little of both. Yeah, follow.
So does the land become more valuable because now it's a source of clean electricity, and how is that value realized in the marketplace?
Yeah, so it certainly is. Generally farmers, specifically in the Midwest, love wind because it's an added revenue stream for them. Now they need to balance that with, they're not the ones typically developing it, so there's a developer who's going to, make sure that they have access to all the capital and take a lot of the risk of the project. So they need to make sure that they're going to make enough returns on their piece of the puzzle and wherever their investors need. So then that sort of, based on the structure of the marketplace and how much money I'm getting for the electricity I'm generating, will dictate, to some extent, the market conditions will dictate how much I could actually afford to rent the land or lease the land for.
That's why I asked the question about the percentage, because if you grow up on a farm, any farm would have a brain to figure out, is it worth X dollars to lease, extra on it.
Yeah, I think, in a lot of cases, there's been a lot of success stories with the farmers in the Midwest in terms of this is a really nice value stream for them in terms of, they look at it in terms of that's a resource that they to some extent own, right? Because that's the piece of land they own, and they're happy to get a payment for that. But they typically aren't the ones who are developing the site. So there's there's all these different pieces to it, and they all need to make their piece of money. And there's only so much. When you look at it, right, the market conditions will say how much money is available to split across all these different places. That help?
Well, saying that the farmer retires and sells the land now, isn't it a lot more valuable when he goes to do that than when he started out?
Yeah.
Absolutely. Or you can do it this kind of cash flow calculation and say my land's worth this much.
Yeah. No, I think it certainly would be, right? Because they understand that there's a true revenue stream to be accessed somehow by someone. Maybe they can't do it themselves, but there's a revenue stream to be accessed on that piece of land. So there's certainly that land becomes more valuable. Now, that piece of land becomes more valuable based on the price of electricity in the marketplace, which may fluctuate based on the incentives, which may fluctuate based on the price of natural gas. So there's lots of things that can go on, right? So it's not it's a one. I'm just going to touch on this piece real quick, which is there's differences in the technology among the different OEMs. So remember I talked about it before. Blade materials, so specifically are long. So typically there's a load-bearing member within the blade. Sometimes it's a box, sometimes it's an I-beam. In this case, it's an I-beam. And one of the most important things on blade design is the tip deflection. So you think about the stiffness of a blade. So if I wanted to make this blade really stiff, typically what's done historically is you just make these fiberglass I-beams, right? The one idea is I could take a heck of a lot of weight and cost out of my blades if I moved to carbon fiber, right? Because it's a lot lighter, very, very stiff. I don't have to use as much. Problem is now you just balance that between the added cost that you have. And now you have introduced a new material that you need to make sure you go through the whole O&M perspective on as well in terms of how do you make sure that it lasts accordingly. So between the industry, there's different blades have either glass or carbon, and that's basically a differentiator between some turbine manufacturers, and even within GE, we have some blades that we have carbon in the field and we have glass in the field. So there's a big difference there. One of the big ones you'll see across the industry is the drivetrain architecture. So here's the traditional one I showed you before, the geared, and here's a look at a direct drive unit where you have the big generator in the back. This is a GE cutout of what we would think our direct drive generator might look like. We're really focused on the geared solution. You get into really, when you want to really compare these, you don't just look at the cost associated with them, you have to look at the efficiencies. And not only the efficiencies of the gearbox and the generator, but now do I have different power conversion efficiencies that I need to transfer through the whole system? Now have I changed the mass up tower? And I have done that, so now I might change that might change my foundation and my tower's design. So it really propagates through in terms of not just the gearbox versus the added cost of the generator. You need to go through efficiencies, you need to go through the loads it's going to see on the rest of the structures. So it really becomes a lot more complicated. And also you'll see different things in terms of material on the generator. So on the direct drive generator, they often need rare earth materials, which have big fluctuations in price based on supply and demand of those metals. So that's something that you have to factor in too. So it becomes a very complicated comparison, but you'll see the industry sort of split in between. Some manufacturers are doing some direct drive, and some are more traditionally like geared, like GE is very much in the geared camp. There's some differences between the power conversion and controls, which I sort of talked to before, but I'm going to move on based on the time here. So remember we talked a little bit about different ways the wind farms are laid out. Here's some basic wind turbine spacing rules. So if you have a predominant wind direction, you'll want to keep the turbines perpendicular to that, 3 to 5 rotor diameters away from each other. Say if 100-meter rotor diameter, you're saying site these things 500 meters apart. So that's quite a bit apart. Spacing, if you have a predominant wind direction, you might want to space these things farther apart so the wake effects and specifically the turbulence associated with the wakes move out, and you don't see that on the incoming turbines. So you see a lot of those arrays, which I show here, where you basically have rows and rows of turbines, basically a big matrix. Then you also have them along ridge lines as well, so you might have more of a line type turbine. And in fact, this is a generalization. You might have a site where it has a few hills, and you have a cluster of them on this plateau, and then you have a big valley, you have none, and then you have some other ones, and it doesn't necessarily have to follow these rules either.
What made you decide not to put those just in a straight line looking down to the horizon?
Yeah, that's a good question. Who knows what it was? It could have been, it would have been nice from this picture, but. All right, this is one of the most famous wind turbine pictures. This is an offshore turbine farm, and it happened early in the morning. You can see that there's fog generation happening, which really shows you what's going on in the wakes. And this is, I would say, relatively poor sighting of turbines, right? So you can see that the predominant wind direction is the one turbines are being waked right into the other, and that's just aggregating into wake effect beyond that. So this is really a nice picture, which we typically can't see because the wind's nice and clear, but this is a nice picture of how these things propagate. And there's actually a big interest within the wind industry now in understanding and modeling this behavior in terms of not only how do I sight these, but do I operate my front turbines a little bit differently so I can extract more power on the backside of turbines as well, or the turbines behind. So it's, the fluid dynamics and the modeling that goes on this level is really quite complex and really cutting edge. So it's really exciting, some of the stuff that's going on here. All right, I'm just going to quickly touch on the economics of wind. So there's probably a lot here, but left-hand side there's an LCOE chart. I show onshore wind with some different on LCOE. So just onshore wind by itself is probably around 6 or 7 cents per kilowatt hour. On the order, that'd be $60 or $70 per megawatt hour. In the U.S., you get a depreciation, and pretty much most places you get an accelerated depreciation schedule, which is fancy terminology to makes your capital a little bit less expensive because now I can depreciate it faster and makes my taxable income look lower in some of my front years of my project. That's really an incentive that people typically don't think about that's there. It's been there, it's nice and steady. It's been probably in the US for 25 years, the maker's depreciation schedule. But that certainly has a nice impact. It can drop it down a cent and a half. And then you have the production tax credit in the US would drop it down even lower. And this is, when you do LCOEs, you have to assume some sort of wind speed. So obviously if the wind speed improves, you can drop these all down. If the wind speed gets worse, they go way up. Right? So it's really all dependent upon the site wind speeds pretty heavily. Here's some looks of what the cost of offshore is in terms of LCOE. So you can see the big gap that you're seeing between these. Again, the big problem is, yeah, you've got a little bit better wind resource, but now you've had this a lot of extra added cost in terms of the foundation. Often the foundation costs as much as the turbine. So that's how expensive these foundations are, especially if you get into about 20 meters of water depth. The foundation can become as much as the turbine, and you have to transmit all that electricity to land, and maybe you're 10 kilometers from shore. So that becomes a big added cost and shoots that way up. Important incentives, there's really production-based ones like the PTC in the US. In Europe, they have feed-in tariffs. Really are the things that have driven a lot of the wind installations. You can see that you're probably pretty close, even without the incentives, to competing with natural gas. You're close, maybe not all the way there in the US, but you're really close. And in a lot of cases where natural gas prices are a little bit higher, you're probably there in terms of economically competing on an energy basis. There's also the installed cost-based ones, which is typically mostly the accelerated depreciation. For a short period, utility scale wind was able to apply for the ITC, which solar does, but that's gone away. The second piece of the economics puzzle is that pretty much every turbine manufacturer has a different product for North America than they do for Europe. And in fact, GE now has more than one product for each of them, right? So we're really nice and good that way. But in North America, you typically have a lot of land available, although not the case. So you have big project sizes, often more than 50 turbines. You're competing with really low natural gas prices, so you get low PPAs. And you get decent wind resources. So you really want to manage the cost and get as good of performance as you possibly can. So you're really looking at generally the lowest LCOE to a really simple extent. I mean, it goes off of that a little bit. And you can see the different products we have for the North American market, anywhere from 1.7 megawatts to 2.3 megawatts and 82 meters to 107 meter rotor diameter. So that's a nice mix for the US market, and that's always changing. I'm sure we're going to add some new products soon. European side, a lot lower project sizes, typically worse wind speed, but they get really good feed-in tariff, so they really want to pay for energy. They say, you know what, it doesn't really matter if I get the lowest cost electricity, just give me something that produces a little bit more electricity because I can really extract value out of that based on my feed-in tariff. So you'll see you can increase your size based past where you would really optimize for your LCOE. And you see bigger turbines, specifically on the nameplate, 2.75 to 3 megawatts, 3.2 megawatts, and up to 120 meter rotors. If you looked at some of our competitors, you might get to 130 meter rotor diameters. So this is really bigger size turbines will be in Europe because of these big feed-in tariffs. All right, I think this is my second to last slide. So this is about perfect on time while I get a few questions in. Generalization on current research trends. So there's obviously lots of detail going on that I can't include in one slide, but how do you cost effectively scale? So here's a picture of blade layup, and you can see the little people standing inside the blade, right? So this is how do you cost effectively scale up the blade? How do you transport it? These are big questions in terms of materials, in terms of structural design, in terms of aerodynamic design. A big interface between all three of those disciplines in terms of blade design. And it really translates all the way back to towers too. That's more of a mechanical design. Here's a truss type structure that we have called a lattice tower that we're putting up, a space frame tower that we've done some demonstrations on in California. But basically we have a truss type structure that we wrap instead of having just a straight tubular tower that we think we can shave off a lot of the cost of the tower. There's a lot of work going on in terms of farm level optimization. I talked a little bit about some of the wake effects in terms of modeling those, but there's also a lot of data that you have at a wind farm. How do you take the big data analytics and map that in terms of how do I best extract value out of this wind farm? Do I look at how one turbine might be performing versus another, if there might be some sort of O&M problem I need to look at? Should I tell if one of the upcoming turbines sees a gust, should it tell the one downstream so I can manage it a little bit better and reduce the loads? So there's a lot of work going on in terms of how do you manage across the farm really smartly. And the analytical push now and the big data kind of push is really at the forefront of this piece. There's quite a bit of work that we do in terms of added sensors and how do you add new control strategies, and how do you manage loads? You know, because if I can reduce my loads, I can reduce the cost and maybe scale up a little bit more effectively. So there's a lot of work going on there. And likewise, you know, we didn't really talk about it, but there's the variability of wind and how do you make it grid friendly. So GE's done some work in terms of integration, some small amounts of energy storage with wind turbines, specifically to try to make it more predictable, you know, how to firm it up, and not necessarily over like days or months, but really over short time frames, like say 10 minutes. How do you make it more predictable for 10 minutes? Because there's a lot of value, we think, for grid operators over that short time frame that really shorten it up. Say, yeah, I can't tell you what I'm going to be producing an hour from now, but I'll tell you in the next 10 minutes I'm going to be here within plus or minus this little bit of a tolerance, and I'll keep it that way.
When someone dies, how long does it take for the power to kill off? You got this whole sort of issue of power.
Yeah, it's in the order of, it's not in the order of minutes, in the order of seconds. Okay, it's on the order of seconds. It depends, but again, you don't extract it on one wind turbine in a matter of seconds, but you might not see that later in the farm until a little bit later because of the size of a farm and how it's laid out. You might see some aggregation effects as well.
To what extent can the firmware in the turbine be updated once they're already in the field? For instance, if you come up with some new optimization strategy in which the turbines communicate, can you apply that to once they're already? Yeah,
we've got a big, GE's got a big market in terms of not control strategy updates, in terms of, oh, we think we can provide value to you by keeping the loads down a little bit lower, and we're going to allow you not to max out at 1.6 megawatts, but we'll power you up to a little bit more. And we can allow you to extract more value. Now you're not a 1.6 megawatt turbine, you're a 1.65 megawatt turbine. And yeah, that's a small amount, but it can, over a year, you can really extract value out of it. So we certainly have the ability to whatever software constraint we have in a turbine, right? So it's like, you know, if you need to do something that the current hardware in the turbine can't handle, then you need to potentially also upgrade that, but a lot of times that upgrade cost may be worth it.
So in the Midwest, you know, where they sometimes have tornadoes and stuff, obviously if you get a direct hit, it's going to wipe it out like it wipes anything else out. But you get pretty high freak winds, and they're maybe to the maximum. These things kind of fall over.
I mean, so we designed them for those IEC standards. Those IEC standards are typically not tornado-driven maximum winds, but I don't know of any turbine that's taken a direct hit from a. Well, maybe I should just Google it and find out, but I don't know. I would suspect it wouldn't last. Occasionally, there's a problem with a wind turbine, and you'll see a turbine fall over. Very infrequently. And it's obviously a big news item because, you know, everyone likes to see it, and somehow there's always a video of it. But they're very infrequent, and typically they're mostly due to some sort of manufactural defect that has occurred, right? So those things are very infrequent, but at the same time, you know, they're also very easily seen across a population, right? So it becomes a big thing. Yep, in the back.
Do you have to have design where you have integrated turbine with gear and generators and water condensers, where you can actually, you know, collect the water at the high pressure when you are winning the wind energy?
Yeah. So we, you know, the way we've designed wind turbines today, and the focus that the industry really is looked at is just how do you make electricity. So there hasn't been integration with, you know, I want to do something else with any power that I have, or any collection of water, anything like that. So, and I think, you know, to some extent, it's because we value, you know, the customers we have value electricity, and the way they think about wind turbines as electricity generation. But also, you really need to understand, if I'm going to be doing something else with it, how much impact am I reducing in terms of my electricity production to do that, and is it really worth it? So you really would need to cross that barrier to make it economical. But today, I think the industry is really looking at, how do I make electricity? How do I make it cheaply? How do I make it compete with other forms of electricity that are out there, which is, you know, it really is on that, it's on that margin of competing really well, even at low gas prices. So it's really, really close to being like, totally mainstream and incentive free.
Could you comment on powerless wind, like the Google private project and tethered things, and is this going to take off? Is this 20 years out, or is this something that is still needs a lot of development?
Well, I think it's early, right? So those things are early in development. These turbines are relatively mature. We're doing incremental changes, incremental improvements to these. I think it's too early to tell how those towerless wind turbines will do. So obviously there's a lot of, the good news from those things is you're able to go up higher, extract higher wind speeds. It can be a little bit smoother with less turbulence. The real challenges are now you have, there is a cost for doing that. Yeah, you don't have a tower holding up, but typically you have some sort of wires to do it. And the control aspect of that becomes very, very difficult in terms of how do you control that in a very safe manner, and then how do you make it cost effective with something else. So how do you position the wind turbine to make sure it's always positioned the right way, and how do you yaw it and make sure that it handles all those things. There's a whole controls aspect that really needs to go. I think some of the stuff that's been done like Makani or some of the other towerless wind turbines are really neat ideas, and they're really early in terms of development, so it's really too early to tell, but there's certain challenges and things they need to overcome. I think the proof of concept, yeah, you can create energy up there, yeah, I can do that. The question is, can you do that? Can you follow standards? Can you make the control things work? Can you do that in terms of a density that's tight enough that they don't tie up to each other? There's a lot of other questions that need to be answered. There's a lot of other hurdles, but something to kind of keep your eye on as it develops, right? Because that certainly could be something that could be a big change.
Can you talk a little about the long term, specifically rethinking kind of what is the post lifespan? Are these still useful at that point? Is there some sort of upgrade cycle or cost cycle where it's cheaper the second time around? Or is there some sort of end of life where these things could eventually be obsolete because the wind moves or they're in the wrong place or the technology is just...
So, I mean, if you looked at over a long-term period, right, so we talked a lot, there's a lot of stuff about climate change this morning and the effects, right? So if you change wind patterns, obviously you could have a lot of wind turbines. If you had huge changes in wind patterns, you could have big effects on where these things are sited. Typically, the project lengths are done around 20 years. Most turbines installed today are less than 12 years old. So, we really haven't gotten there, so we don't really understand all of those things. But I think the industry will start to understand how long you can go. So you typically design these things for 20 years. Not to say something's not going to break at 24 years, so you can keep running it, or something's going to break majorly at 16 years. I think typically what we've seen with, I think would happen with customers is, something small that broke that you could fix in a relatively economic way, you would fix. If you had like a big gearbox failure, which it's multiple hundreds of thousands of dollars to fix it, then you might say it's not worth it because to pay off that investment to do, it's going to take me another 7 years, and I think that I might have something else of a problem. So you'll start to see the decisions made on a turbine by turbine basis in terms of what's breaking. I think you run it until something really breaks, but they're designed for 20 years, and I think the industry still just really hasn't gotten there because most of the wind turbines we put in has been over the last 5 or 10 years. First.
Okay, this is a climate conference, and before you've even gone online, you've done the design, you've built blades, you've powered turbines, you've transported them, you've done an installation process. Is there a rule of thumb about when you're no longer carbon negative, but you're carbon neutral? How long does that take?
Yes, that's a good question. So I'm not the expert in that, and I don't think anyone at GE is the expert, but I think there's other sessions that have done some work here. So I don't know that answer, but I know that wind turbines is over the life of a turbine an economical way from a carbon perspective. Over the 20 years, it's certainly carbon negative. So there definitely is a crossover point, and I don't think it's at year 19. I'm pretty sure it's not like just barely carbon negative, right? So I think it's it's moved up, but I don't have the exact number. I would suspect it's somewhere between 5 and 10 years, but you know what? That's probably just me guessing at this point, so I'm sorry to say.
A couple of questions. First, can you comment on the various blade configuration of vertical, horizontal movements, blade shapes, and when they affect on applications? Second is about the rooftop systems, and they be made cost effective.
Yeah, so the first one, we talked a little bit about, so the industry's really looked at the CPs of horizontal axis wind turbines as being significantly better than vertical axis wind turbines. And really has gone down the path of 3-bladed. So there are some places where you might see a 2-bladed machine, but really 3-bladed is where the industry is converged, and it's very difficult for me to see any major change off of that. The vertical axis ones, I mentioned that they have a lower CP, so for them to compete with the horizontal axis, they would need to be a lot lower cost, which today they aren't. Now, Sandia is doing a lot of work on offshore vertical axis wind turbines, where the idea is that you could extract some low center of gravity pieces from the vertical axis wind turbines and extract some value out of the rest of the balance of plant system and get some lower costs. So maybe there's a play in the really large offshore wind turbines for vertical axis. Now for residential scale, the CP or the aerodynamic efficiency are really all over the map based on the different manufacturers. So it's difficult for residential people to really understand how efficient a wind turbine is, and it's really more about what's the cost and what do you think your power curve looks like, and what is it going to look like for me? In some cases, if it's small enough and the loads aren't enough, you could potentially put it on top of a rooftop. So there's some things there, but you need to think about the tree levels as well, because you get a lot of dampering of the wind based on the trees. So even if your roof's up relatively high, if you have a lot of trees around it, so it becomes a really micro-siting type application for residential use, which is very hard for a residential person to really understand or to do appropriately. Besides looking around and saying my trees at my house are taller than my roof, so I probably shouldn't do this, or I don't have that many trees. So, to really understand the wind resource, it's difficult.
Actually, rooftops or big box schools, rooftops are pretty flat and few trees around.
Yeah, well, even there you get a lot of slowing of the wind based on just the box store itself. So, generally I would think you would want to have a wind turbine significantly above that to get rid of some of the dampering of the wind. So, I think till today you don't see very many rooftop wind turbines. I don't see a lot of that happening. Maybe I'm wrong. The only place you could see it is if you had, you're borrowing the cost of something else. So like a light tower or something. I want to, I'm doing lighting up a parking lot. I want to use those light towers, and I just need to strengthen it a little bit, and I can put a small turbine on top of it. And now you're starting to, borrow a cost you're using for something else and making your system a little bit cheaper. I think I just had one more thing to show you, and then we can take the last questions, which is just this, just my advertisement for GE is we actually have a lot of stuff online, and I, really want to make sure I advertise that there's a lot of cool stuff that we do at the Research Center, not just on wind, which I really care about, but a lot of other stuff too. So, there's a lot of things to do, and you can really interact with some of the researchers and see what we do, and I do encourage you to take a look at that. I'll take a few more questions, I think.
Touch on pieces of the question I'm going to ask, and it's really a company-wide or systems-wide question. But given the importance of intermittency as the principal obstacle to better use of wind power, what activities are going on within GE where the issue of how do you store, at least for some period of time, the energy that's generated, whether it's battery storage, whether it's fuel cell, whether it's moving water up so you get hydro effects, whether it's heating water to retain power. But it's so important for wind to have raw ability that we get the storage piece of the equation right.
what's going on, and does it really require different ways of designing the turbine so that you get the effectiveness that we need longer term in order to have wind play a bigger piece of the total energy equation?
So I answer that way in a lot of different ways. One, at a wind business level, there's a lot of activity going on in terms of adding small amounts of energy storage to do short-term predictability. So firming up short-term. So I talked about it before, say in the order of 10 minutes. So I don't need to add that much energy storage to do that. I can look at different technologies of energy storage and I could pick about it. It's going to be small amount of storage compared to the size of my wind turbine. So I can keep it relatively small amount of a cost adder, relatively small, and get a big benefit, I think, for the grid. Because I think the grid has different problems with intermittency. One is the really short time scales, where they're handling big differences in terms of you're bouncing up and down, and my, I need to follow this with some other load generation resource. And then there's the longer term stretches where I'm going to try to power something 80% from wind, which I need to make sure that I have some sort of capacity, capacity adder. So, yeah. So I think on the first side, there's a lot of activity going on in that short time scale, because I think from a GE's perspective on what's most valuable to the grid today and what's valuable for our products today, we certainly have that. Now, GE as a whole understands that energy is a really important aspect, not just for energy storage is a really important aspect. So we have an energy storage business where we have our own battery that we've created and we're working on manufacturing that could be used for some a little bit longer term durations. We have fleets of gas turbines that can ramp up and down and provide relatively clean power as well. So we're not trying to necessarily pick the winners and losers, but have a nice portfolio of technologies, depending on which ways the costs and the prices fall out, to handle some of these things. And one of them is hopefully the wind keeps increasing in penetration, and hopefully we have this problem. That means we sold a lot more wind turbines on the way, and we can, we have our hands in energy storage. We have our hands in terms of really efficient gas turbines that can cycle up and down, and we've done a lot of work on that. So we've got other ways to try to manage that to some extent. So I think there is a lot of activity. I think on the wind business itself, in terms of integration of wind and energy storage, in a sort of a own package, it's really currently around that short-term predictability. Although you really want to look at the markets and let the markets dictate. If there's a reason for longer-term storage, they just need to make sure it have the right value associated with that, because there's certainly solutions that can be done. It's just the price doesn't meet what the people are willing to pay for it today.
A few years ago, there was a published paper that addressed the intermittency issue of problem with wind power by going to synoptic scale of wind turbines. And has GE done any similar studies of synoptic scale wind power vis-a-vis the costs involved and the et cetera, et cetera?
So I don't know at that level. I know, so we have a lot of different businesses and a lot of different places. One of the places we have is within, it's called GE Energy Consulting, which they do different consulting jobs around this. And I know they've done some studies around integration of renewable assets to different penetration depths. I don't have the details off the top of my head, but I think that they showed it. It's clear that at today's levels, you really don't need specific. Relatively the grid can handle some of the fluctuations of the wind because it's at low enough amounts. And at a certain point, you're going to see some really big transitions. And I can't remember what that point is, but we certainly have done some work in terms of looking at that market. But that's more of a market look in terms of how the grid's going to work in terms of that. So we certainly do some work in that, just not at the research center as much.
Because that paper claimed that having a synoptic scale wind farm offshore from New England all the way down to Florida, that can address the
intermittency.
resort
Yeah, I mean, if you site these things far enough apart, I mean, you already get some, you get a lot of averaging out. So if you looked at, if you looked at predictability at one wind turbine, it's really, really hard. You start to spread it across a farm, and if you spread it across the entire grid, it becomes a lot easier to some extent, right? Because there's still like node challenges and stuff. But I think you had a question here.
So has the U.S. government cycles personnel and support for wind and other renewables varies? I'm curious, how much does GE experience that? Is someone insulated or?
No, it's a huge effect. So if you looked at the wind installed in the U.S., which is a huge market for GE wind, it's like great, small. Wait, that's when the PTC dropped out. It's great again, small. And it's just the politicians want to make sure they get involved, and we're paying attention to them, I think. But it's really, that PTC is really not that much compared to some of the incentives they get in Europe. But it really is that difference between a lot of it installed and not a lot installed. Specifically, like when they say that the PTC is going to be cut off at the end of a certain year, and then everyone says, well, I got all these places I want to put wind up, but I got all this uncertainty after this year. So let me just do it all this year, and then I just, it's like this mad rush. And then even if the PTC is extended right at the last minute, you get a big dip the next year because, oh wait, I've just done all the ones I wanted to do. So it's, it's all right. I just need a break here before I figure out some other places. So even when they, renew things at the last minute, it becomes a problem in terms of the market. Now, the marketplace insulates itself to some extent because we're not totally dependent on the U.S. market. There's a global market, right? There's a lot in Europe. There's some in Canada. There's some now in Brazil. There's you see a global market developing, so that insulates you to some extent. But certainly, U.S. is a big portion of the market, so you still see big dips. Is a big disruption in business models.
Just wondering if you see a market for a homeowner 5 kilowatt wind turbine, and do you have any need for that?
So GE doesn't have anything for that. I would say there's going to be 3 things that you really need to have. One is a relatively good wind resource. I mean, not to the extent of these things, but you can't have like a not windy place. You need to have relatively high electricity prices at home. So don't think the Midwest, because they're pretty cheap to get electricity. And it's nice to have some incentives locally. So sometimes you can get like a state will have like a little incentive. I think California is relatively good in incentives typically, which can bring down the cost of the residential unit and if you get sort of those 3 things coming together, you can sort of make the economics work, but it's difficult.
Yeah, small turbines are hard, right? Very efficient.
In terms of efficiency, in terms of the cost, I mean, it's a tough economic case. You can sort of make it work if you get those 3 factors coming together, but it's difficult.
I've heard in the past that you've got a rotating system here that generates cyclic sort of things on the grid. And in the past, there's been problems on the grid with resonances from wind turbines. Is that still an issue?
I mean, there's been a lot of work going in the way we convert the power and making the wind turbines more grid friendly. So I think, there's no big hang-ups in terms of wind integration in terms of grid codes today. And I think they're really, really solid. Certainly, through this big ramp up, we've gone through a lot of learning and we've gone through a lot of developments. But I don't think that's a big issue we see currently today. Okay, one last question and we'll cut it off. Thanks.
On the question about penetration, what examples are there of national or regional penetration levels, and how high have they been in kilowatt hours out of the building?
Well, I think, the trick is between, how much energy is produced and how much capacity is added. So like last year, I think maybe in the US, maybe 30 or 40% of the new capacity added in the US was wind. Now, if you extract that back to capacity factors, that probably means of new energy created based on these new things, it's probably 15% of the new energy was added because, these things aren't operating base load. But you see that they can be a relatively big amount of new additions. Now, the electrical grid is so big that, new additions every year, even though if you get big increases in wind, it could still be a relatively small amount. So I think in the US, we're, 2 or 3% of capacity is wind or something like that. So it's still relatively small, but it's growing quite a bit.
How about Denmark, Germany?
Yeah, so those have gone, I think Denmark might be up to 20% or close to 20%. Germany's not quite as high, but they've got a really big installed base of wind. So I mean, you certainly see a lot of the European countries a lot higher penetration rates than the US. Well, thanks a lot. I'll stick around. Appreciate it.